Welcome back to IT 3000. Today we're tackling one of the most important pieces of software you'll ever encounter, the operating system. Think of it as the layer that transforms a pile of silicon and spinning disks into something we can actually call a platform. Because without it, every single program you wrote would need to know the exact brand and model of your hard drive, and nobody wants to live in that world. So let's pin down the concept. An operating system is the piece of software that manages the machine's hardware resources and offers a consistent set of services to the applications running on top. That means your programs can happily run without knowing a single detail about the specific chips or drives underneath. Put simply, the OS is a resource manager and a translator. It decides who gets what, and it hides the hardware behind a stable interface. So how does that resource manager actually earn its keep? It boils down to 4 ongoing jobs. Process management decides which program gets a slice of the CPU and for how long. Memory management hands out RAM, keeps programs from stepping on each other, and shuffles pages to disk when things get tight. The file system turns raw blocks of storage into the neat hierarchy of files and folders you actually recognize. And device management uses drivers so every app can talk to a printer or a disk in exactly the same way, no matter the brand underneath. To see how all 4 jobs fit together, picture the operating system as a stack of layers. At the top sit your applications, running in user space with deliberately restricted rights. Below them is the system call interface, the controlled doorway an app must knock on whenever it needs something real. Behind that door lives the kernel, with its scheduler, memory manager, and file system, which in turn speaks to device drivers, and only then to the actual hardware. That boundary between user space and kernel space isn't bureaucracy for its own sake. It's exactly where isolation, security, and stability are enforced. Let's watch that stack come alive with something you do every day, double-clicking an icon. First, the shell asks the kernel to create a process, which gets its own PID and a private address space. Then the loader pulls the executable and its libraries into virtual memory, but lazily, only the pieces actually needed. The process joins the ready queue, and the scheduler decides when it finally gets CPU time. While running, it makes system calls, each one a controlled trip across that user-to-kernel boundary we just discussed. And when it exits, the kernel tidies up, reclaims memory, closes handles, records the exit code. Nothing is left behind. Now, a quick clarification that saves a lot of confusion later. People casually say Linux to mean 3 different things, but they're distinct layers. The kernel is the privileged core, always in memory, managing resources and speaking directly to the hardware. The shell is just the interface you type or click into, and you can swap it out without ever touching the kernel. The operating system is the whole package around them: kernel, shell, libraries, utilities, and usually a graphical environment on top. When something breaks, knowing which layer failed is half the fix. With that foundation in place, everything ahead becomes a closer look at the pieces we've been circling. Each of these, process, kernel, file system, virtual memory, device driver, and virtualization, is a specific job the OS performs as it manages resources and translates between hardware and software. Next up, we'll zoom in on the process, the running unit of work that everything else in the system ultimately revolves around. So let's lock in the essentials before we move on. An operating system is always doing 4 jobs at once: juggling processes, managing memory, organizing the file system, and talking to devices. The split between user space and kernel space isn't accidental. It's the boundary that keeps the whole system secure. Remember, the kernel is the core, the shell is the interface, and the OS is everything bundled together, the layer that turns raw hardware into a platform you can actually build on. Next lesson, we go deeper into processes. See you there.